Welcome to this movie on statistical mechanics. I am Jos Thijssen and I've made this movie. It's part of a series of movies I've made for the students I have in statistical physics at the University of Delft. This movie is about the Grand Canonical Ensemble, and the Grand Canonical Ensemble is used to describe systems in which the number of particles can vary. You can control it with a parameter, it's called the chemical potential, but the number of particles is not fixed. The temperature is fixed, so you can use that to control the energy. And in order to follow the analysis here, it's important that you know about the canonical ensemble first. So you can consult my other movie which I made on that topic. And I hope you enjoy this movie. Before we really go into the Grand Canonical Ensemble, let's recall how we constructed the Microcanonical Ensemble. The Microcanonical Ensemble is an ensemble of systems which all have the same energy, so we fix the energy and the temperature can then be measured. The alternative way of dealing with energy and temperature is the canonical ensemble, where we fix the temperature and we can measure the energy, and the energy can also be calculated when we know the free energy. E is minus t squared df over t dt at fixed n and v. So what do we do in the Grand Canonical Ensemble? Well, first of all, we fix the temperatures just like we do in the Canonical Ensemble, and we can measure E. But there's also an additional thing we do, and that's the following. Now we don't fix the number of particles, but we fix mu, which is the chemical potential, and then we can measure the number of particles. So we have introduced now a parameter which is called the chemical potential, and it can be used to control the number of particles. The way to derive the ensemble in detail is via the Shannon entropy, which is generally defined as S is minus KB times the sum over all the states which are labeled R, and then we have PR and the log of PR. Now R is a state of the system, and if we don't fix the number of particles, the state is a state for n particles, but we also need to include different choices for n. So we are going to refine the description of the states. The PR that we had in the canonical ensemble, for example, is now replaced by a P which depends on the number of particles, n, and Rn, which is a state of the n particles in the system. So what we want to find are these p's which now depend on n and on Rn, the state of the n particles. And the condition to find p are the following. First of all, we search p such that the entropy is maximum. The entropy defined over there. And the p's should be probabilities, that is, they should add up, of course, to 1. That's a normalization condition. Then we want the energy to have a fixed value, the expectation value of the energy, that is, it should have a fixed value, and so this is the expectation value of the energy, obviously. And the number of particles, if we take the expectation value of that, we also want to have that fixed. And then we will find Pn's, and the Pn's will involve several constants. There will be a constant controlling the energy, and as you may already expect, that is the temperature. And there will be another constant which controls the number of particles, and that will be the chemical potential. The technique for finding the maximum of the entropy and subject to certain constraints, which are listed here, 1, 2, 3, is well known. We use Lagrange multipliers. So the entropy, which is the function on the right hand side, is the function to be maximized. But we have to add terms which represent the constraints. And so the first of these is the normalization of the constraints, which has a Lagrange multiplier lambda. And then we have the term which fixes the expectation value of the energy. And this has a constraint KB times beta. So at this time the beta is just a Lagrange multiplier which has by convention this extra factor of KB along with it. And then finally we have a term which fixes the expectation value of the number of particles, which you can see here, and that also has a Lagrange multiplier which up to a factor of kb and beta is given the name mu. And if you want to maximize this function, obviously we have to take the derivative and put it equal to 0. Here I've done this. The first two terms derive from the entropy. Then there is the lambda, which derives from the normalization condition. Then there is the term from the energy, and then there is the term from the number of particles n, and that should add up all to 0. And then we have an explicit equation for the Pn, so we know what it is, and the result is P, depending on n and on Rn, is a constant times just the Boltzmann factor e to the power minus beta e, and then there is this additional factor which involves the number of particles, beta mu times n. So what about the constant? We have to choose the constant such that these Pn Rn's are normalized. And so we can write this constant. We give it a name. It's 1 over z grand, and that's the so-called grand canonical partition function. And this z grand can be evaluated, and it has the form z grand is the sum over all the particle numbers and the states for each particle number. And then there is this Boltzmann factor, and there is this extra factor of e to the power beta mu n. And we see that we can just perform first the sum over the n's, and we can then write this expression as e to the power beta mu n. And then we have a sum over all the particle states of n particles with the Boltzmann factor. And if you look at this expression, if you consider the second part of this expression, then you will recognize that this is nothing but the canonical partition function for n particles and at temperature T. And there may be also a volume dependence or a magnetic field dependence or whatever. We can interpret the P and also the grand canonical partition function as follows. There is a certain weight factor which is e to the power beta mu n for having n particles. And there is in addition a weight factor within each number of particles which is e to the power minus beta e n Rn. So that's just the Boltzmann factor. And it tells you how likely a certain state of n particles will occur, provided we have indeed n particles. Now, having this result, we can calculate whatever we like, and as an example, we can look at the energy. In order to find the energy, we just start by taking the derivative of the logarithm of the partition function with respect to beta, which in the case of the canonical ensemble directly gives us the energy. But let's see what we get now. We see that we obtain two contributions, one from the beta in front of the mu n in the exponent, and one from the beta in front of the en. And together with the 1 over zg, which comes from taking the derivative of the logarithm of zg, we see that we have two contributions. One gives us a mu n, that's from this term, and one gives us minus en. And so if we look at the expression, we see that this is nothing but the expectation value of mu n, and here we have minus e. So altogether, this implies that we have expectation value of e equals d ln z grand d beta with a minus sign, and then plus mu n. So this is how we can calculate the the energy from the grand partition function, provided we know what mu n is, and mu n is easy to find. Recalling the definition for the grand canonical partition function here, we immediately see that the derivative of the logarithm of that partition function with respect to beta mu gives me the expectation value of n, and that expectation value can be plugged in there in order to find the energy. Let us now define the grand potential in a way completely analogous to what we did in the case of the canonical ensemble. We look at the quantity minus kbt lnz grand in this case. When this is the canonical partition function, it gives us the Helmholtz free energy E minus Ts. And now we get a different object, obviously. We call it Q. It's the grand potential. And a question, of course, is whether we can find a simple expression of Q in terms of thermodynamic quantities. Like in the canonical ensemble, we had the free energy is the energy minus T times S, T times entropy. And so we will look into the meaning of this Q. So if we go back to the grand canonical partition function, we see that it contains the canonical partition function, and we can write this, because it's the canonical partition function, as e to the power minus beta f, where f is the free energy in the canonical ensemble. But we have this additional factor here, and we sum over n. And now we realize that this n is very sharply peaked, so this probability distribution of the n's is very sharply peaked around its average, and so according to the usual procedure we can replace this factor by beta mu times the average value of n. So let's see what we obtain. We then get the following. So here is the e to the power beta mu n star, and from this canonical partition function we get a minus beta f in the exponent as promised, and the stars everywhere, they mean the equilibrium values, and we have replaced the f by e minus ts. And so if we take the kt times the logarithm of this expression, we obtain a simple thermodynamic expression. So here we have done that, taken the logarithm of zg and multiplied it by kbt in order to find q, and the result is, if we include the kbt, which cancels the two betas here, mu times n star minus e star plus ts star, where n star, e star and s star are just the equilibrium values of those quantities. If we then use the Euler relation, which gives us energy as Ts minus PV plus mu n, and put that into this, we have left out the stars now. Then we can quickly verify that Q, which is the kBT times lnzg, is just pressure times volume. And so some books define the Q with a minus sign. Here we use a different sign, so we get P times V. Here I have written Q again in its original form, mu n minus e plus ts, because that's very convenient for finding the differential of Q. So let us consider dq, which is mu dn plus n d mu. For the energy we use the first law, so that gives us minus t ds plus p dv minus mu dn, and then we have plus tds plus sdt, and in view of the fact that we have now plenty of cancellations, like this term cancelling against that term, and this term cancelling against that one, we are left with n d mu plus p dv plus s dt. And so we see that dq is an exact differential of these quantities mu, v and t, and we can immediately write that the partial derivative of q with respect to mu, while we keep the v and the t constant, gives us n, and we obtain similar expressions for the partial derivatives with respect to v and t. So here they are all together. So you should compare these equations with the expressions for the thermodynamic quantities in terms of derivatives of the free energy in the case of the canonical ensemble, of the derivatives of the entropy with respect to the system parameters in the microcanonical ensemble. Let us now move on to an application where we have a gas which is in equilibrium with a solid. This means that the particles, the blue guys here or the blue guys there, they're all identical atoms, but they can be either in a solid form or they can be in a gas. And we first ask ourselves what the potential would be which the particles feel in the solid. So in the gas they are supposed to be free. That's usually a very good approximation. But in the solid they are obviously bound to the other particles. And so they are probably in some potential well, which I will now try to draw. The well is approximately parabolic, and we assume that the bottom of the parabola is about epsilon 0. And we furthermore assume, well, you can make different assumptions, but you may assume that there are quite a few harmonic oscillator levels that are accessible to the particles before they go out of the well. So the difference with the real harmonic oscillator is that at a certain finite energy the potential becomes flat, and so the particles who are deep in the well will hardly feel that, but the ones who are here, they will feel that the potential here is not going up, but that it's flat. Furthermore, there is obviously a curvature which tells you how quickly the particles would oscillate classically. It's characterized by an omega, so that the curvature here tells you how quickly particles would oscillate in the classical state. So if these two systems, the solid and the gas, are in equilibrium, we would like to have that the mu of the solid, so the chemical potential of the solid, should be equal to the chemical potential of the gas. We have a mu Vt ensemble, so the numbers of particles can be exchanged. The particles can be exchanged between the solid and the gas, but the chemical potential should be the same. So let's see whether we can analyze this system using the theory of the grand canonical ensemble. The first step we make is to calculate the partition function of a single atom in a potential well. And that single atom, we can assume that it has three directions in which it can vibrate. So it is described by a three-dimensional harmonic oscillator, which is a harmonic oscillator in the x and the y and the z direction. And so for the partition function, we can just use the partition function of the harmonic oscillator in one dimension and just raise it to the power 3, as we have done before. So the harmonic oscillator partition function at temperature T, we call that phi. So that's phi, which is a function of T. And we know for a fact, because we have already analyzed the quantum harmonic oscillator, that this is given by kBt over h omega to the power 3, because we have three dimensions. And then we have an additional factor, because the bottom of the potential well is not 0, but it's minus epsilon 0. And so we have an additional term, which is e to the power beta epsilon 0. And so this is the classical result. And for the quantum case, we have this expression, which involves the hyperbolic sign of h bar omega over kBt. Now if we have n particles, each with a partition function phi, then the partition function Zn is just phi to the power n. And I've mentioned here distinguishable, which may be surprising because the atoms are, after all, indistinguishable. Now, this has a rather subtle reason. In fact, as we shall see later, if we want to sum properly over the different quantum states, we can use the framework of second quantization. And in that case, what we should consider are distinguishable quantum states. And each site on the surface is identified with a distinguishable quantum state. And that's the reason why we don't have a 1 over n factorial here. If the number of particles is not fixed, as in this case, the appropriate ensemble is the grand canonical ensemble, and the central quantity that needs to be calculated is the grand canonical partition function Z grand, and we calculate it as the canonical partition function for n atoms. We sum over n and we introduce this extra factor e to the power beta mu n. So this is the grand canonical partition function. And it's very often written in this particular form, z to the power n phi to the power n. And here the z is defined as e to the power beta mu. So that's this factor here. And it has a name, it's called the fugacity. In view of the fact that this is a geometric series, we immediately see that the grand canonical partition function can be written as 1 over 1 minus z phi. And once we have the grand canonical partition function, it's easy to find the average number of particles, so I should put brackets around this to indicate that it's the expectation value. We just take the derivative of ln z grand with respect to beta mu, and we find z phi over minus 1 minus z phi. Now n is the number of particles that are absorbed. The system, it's obviously, or they are the number of particles in the solid. The solid has a macroscopic number of atoms, so n should be large. And the only way n can be large is by choosing z phi approximately equal to 1. So that means that the denominator here is very small. And if that is the case, we see that z is more or less 1 over phi. So in summary, for the solid S, we have that the number of particles in the solid is given as z as phi over 1 minus z as phi, and the grand canonical partition function of the solid is given by 1 over 1 minus z as phi. So let's now consider the gas. The gas can exchange particles with the solid, and therefore it's described also by a grand canonical partition function, which is written here. And the expression for the grand canonical partition function involves the partition function in the canonical ensemble. So we need to fill that in. Anyhow, before we do that, we use the definition that also the fugacity of the gas can be written as e to the power beta mu gas. So mu is the chemical potential, and we have this expression. So let's have a look at the canonical partition function of the gas. The canonical partition function of an ideal gas is v to the power n over n factorial times the thermal wavelength to the power 3n, and please recall that it derives from this full expression. There is no potential because it's an ideal gas, so we have just a 1 here, and this gives me the factor of v to the power n. We calculate the Gaussian integral, and together with the h, the power 3n, and the n factorial, we get the denominator here. So we take this partition function and put it into the expression of the grand canonical partition function in order to find this expression. And if we look at that expression, we recognize the Taylor expansion of the exponential function. And so this expression can simply be written as e to the power zg v over lambda to the third. So this is the grand canonical partition function of the ideal gas. Having this grand canonical partition function, it's not difficult to calculate the expectation value of the number of particles in the gas. It's just the derivative of z grand, of the logarithm of z grand with respect to beta mu gas. And if we work that out, we obtain the expectation value of Ng is given by this derivative, and that leads immediately to this relation between the fugacity, the number of particles, lambda to the third, and v. I've left out the brackets for the expectation value because Ng is a strongly peaked variable. It doesn't fluctuate a lot, so usually we are not too strict about the expectation values. Now we consider equilibrium. And in equilibrium, the chemical potentials should be the same. And because the fugacity is simply defined as e to the power beta times chemical potential, also the fugacities should be the same. So we have that the fugacity of the gas should be equal to the fugacity of the solid. Mind you, this is the fugacity, so it's e to the power beta mu. It's not the grand canonical partition function. This is a lowercase z, in contrast to the uppercase z, which is used for the grand canonical partition function. Anyhow, let's see what this implies. Well, we've just seen that the fugacity of the gas is Ng lambda to the third over v, and from the analysis of the solid, we had found that z is 1 over phi. So let's go back to where we have derived that. Here you can see that the fact that z phi should be more or less equal to 1, which was a consequence of n being large, you can see that here, implies that z is 1 over phi for the solid. And so this is an important relation. And we can combine that with the ideal gas law. We use P times phi is equal to the n gas kBT. We assume that the gas and the solid are kept in equilibrium, so they should certainly have the same temperature. So combining that with the result that we found, we can find that P over kBT lambda to the third is 1 over phi. And the phi depends on the temperature, on epsilon 0, that's the bottom of the well in which the particles move when they are in the solid, and omega, which is the curvature of the potential the particles feel. So we see that if we would measure P as a function of T, and suppose that we know the form of phi, so how it depends on T, epsilon 0 and omega, then a measurement of P versus T could give us information about the curvature of the parabola the particles are moving in when they are in the solid, and epsilon 0, which is the depth of the well the particles are in when they are in the solid. We have just seen how the grand canonical ensemble can be used for studying phase equilibria. And there are many other examples, among which there is the oxygen transport in the blood that also is analyzed in the context of the grand canonical ensemble. And another very important application is the derivation of quantum statistics, which will be done in another movie.